Every day, software systems must process an input space that is mathematically close to infinite. When you combine strings, integers, dates, and user actions, the number of possible data combinations explodes into chaotic, overwhelming complexity. Faced with this scale, many teams resort to monkey testing, throwing random data at a system, hoping to trigger a failure. In an infinite space, this is mathematically futile. It is searching for a needle in a haystack by blindly grabbing handfuls of hay. Data-driven black box design aims to solve this by extracting the absolute minimum set of test cases that mathematically guarantees maximum defect coverage. It achieves this by mapping abstract software requirements into rigorous geometric domains, allowing engineers to target the exact fault lines where code is most likely to break. We are going to trace how this architecture is built. We will start by mapping a single one-dimensional variable, expand that into multi-dimensional matrices, and finally explore how to test the unpredictable parameters of artificial intelligence. By treating testing as a structural engineering discipline, we can mathematically compress infinite variables into a finite, airtight perimeter. This diagram shows the simplest scenario, a one-dimensional specification. The requirement specifies variable x is valid if 10 or less. But look at the code snippet above. They mistakenly wrote if x equals 10. To test this, we first apply equivalence partitioning. This splits the input space into mutually exclusive zones. Anything 10 and under is treated as one valid block, and anything 11 and over is an invalid block. When testing the invalid block, we have to avoid fault masking. If you submit multiple invalid variables in a single test case, the system's error handler might trigger on the first one, hiding the failure of the second. The solution is each choice coverage. This rule dictates that you only ever test one invalid variable at a time, holding all other variables firmly in their valid zones to isolate the exact point of failure. But isolating the zone isn't enough. We have to test the edges. Standard two-value boundary value analysis checks the exact boundary, which is 10, and the nearest invalid unit, which is 11. Here, the two-value approach fails. If we input 10, the broken code passes. If we input 11, the code correctly rejects it, since 11 doesn't equal 10. Both register as a pass, though the logic is flawed. This is why critical systems require a three-value analysis upgrade. We add the nearest valid internal unit to the test suite, the number 9. Watch what happens when we execute 9. According to the specification, 9 is valid, but when it hits the broken code, 9 does not equal 10, so the system rejects it. The test fails, revealing the logical operator bug. While two-value analysis provides an illusion of safety, three-value analysis mathematically ensures we detect these specific logical operator errors. Now, look at what happens when this one-dimensional line extrudes upward into a two-dimensional Cartesian plane, representing two interacting variables like user age and credit score. Standard boundary value testing breaks down here. We upgrade to domain testing, a technique that targets the geometric lines and planes where these variables intersect. We establish these boundaries using precise coordinates. On points are data coordinates placed exactly on the mathematical boundary line, regardless of whether the boundary is inclusive or exclusive. Off points sit just off the line. Depending on the system's precision, whether the logic dictates strictly greater than or greater than and equal to, these points are placed precisely one recognized logical unit inside or outside the domain. To thoroughly test a single boundary line on this plane, we apply reliable domain coverage. This requires plotting exactly 2 on points and 1 off point against the boundary. 2 points verify a line. 3 points verify the slope. If the mathematical boundary tilts or shifts due to a coding error, these 3 specific coordinate dots will instantly catch the deviation. As you add more variables, the geometry becomes 3-dimensional, then 4-dimensional. The number of required coordinate points multiplies rapidly. We control this geometric explosion through boundary sharing. Because these domains sit on a continuous plane, an on-point for domain A mathematically serves as a boundary point for an adjacent domain B. One test case verifies 2 distinct systems. Domain testing replaces guesswork with topological precision, ensuring complex boundary shifts are detected without causing test counts to spiral out of control. But geometry has its limits. When you test a system with a dozen variables, each containing 5 different options, the possible interactions instantly explode into thousands of combinations. This chart plots empirical data from NIST. Notice the massive spike here. 97% of software bugs are caused by the interaction of just 2 parameters. Reaching 6 parameters, the failure rate drops to 0. This is the coupling effect hypothesis in action. It suggests that complex multivariable bugs are almost always manifestations of simple 2-variable flaws hiding underneath. Since we only need to test 2-way interactions to find 97% of bugs, we can use a pairwise algorithm to mathematically compress thousands of inputs down to a few dozen tests. Look at this matrix tracking free parameters. If we ran every exhaustive combination, it would require 8 tests. The pairwise algorithm distills this so that every possible 2-variable pair appears at least once, compressing the suite into just 4 highly efficient tests. There is a critical vulnerability here, though. Pure mathematical algorithms do not understand business logic. Left unchecked, the pairwise matrix generates impossible combinations, like running the Safari browser on Windows. To solve this, we use the classification tree method. This maps the inputs hierarchically, allowing us to explicitly draw a constraint line linking Safari strictly to macOS, mathematically blocking the Windows path. Encoding these rigid constraints into the model limits the algorithm's raw output, forcing it to generate only logically valid real-world test cases. By pairing combinatorial math with constrained classification trees, engineers achieve maximum interaction coverage while entirely eliminating the waste of invalid testing. Up to this point, we have relied on exact specifications, but modern artificial intelligence and non-deterministic systems do not have rigid mathematical boundaries. In these complex environments, bugs are not perfectly randomized. They cluster in localized patches called contiguous failure regions. This topographical map demonstrates how adaptive random testing hunts these clusters. The green dots represent successful, bug-free tests. The algorithm draws a radius from these dots, calculating the Euclidean distance to locate the most isolated blank sector on the map. It uses the feedback of its own successes to intentionally avoid known safe zones, aggressively pushing the test data into uncharted territory where failure regions are hiding. Detecting a deviation in an AI system is difficult because we face the test oracle problem. Humans cannot calculate the correct answer for millions of dynamic inputs, leaving the system with no baseline for comparison. We bypass the oracle using metamorphic testing. Instead of verifying an absolute output, this method verifies the relational logic between the input and the output. In a complex navigation algorithm, we might not know the perfect route from point A to B, but metamorphic testing dictates whatever route the AI calculates. Running the reverse from B to A must yield the identical distance value. By combining adaptive random testing with metamorphic relationships, engineers can validate the integrity of black box AI systems, even when the exact answers remain hidden. While these techniques are used to find bugs in production, their most immediate impact often occurs much earlier in the software lifecycle. The mere act of drawing these geometric domains and pairwise matrices forces a level of scrutiny that exposes logical contradictions in the original product specification. By mathematically modeling the data, engineers spot overlapping partitions, impossible null domains, and missing constraints months before a developer types a single line of code. Throwing random inputs at a finished application fails to meet the complexity of modern software. Today's systems require a foundation of structural data modeling. By architecting the infinite input space early, software teams transition from reacting to failures to definitively engineering systemic integrity from day one.